Welcome back, everyone. Today our goal is to do some more examples related to functions, just so you can get comfortable with the definition and integrate your sense of functions from calculus with your sense of functions from our new definition. So to start with, I want to go through and formally write the rest of the functions that showed up in calculus, or at least a lot of the remaining functions that showed up in calculus, on their natural domains. And for each of these functions, I would also like us to answer the question, what is the image of the function? So let's start with this function e to the x, which is often called exp if you have to give it a name. And so I'm asked here to figure out what the natural domain of this is. And for all of these, I'm going to write their codomain as R. That is, all of these things give out only real numbers, so I'm going to write the real numbers here. Now, again, they might not give out all real numbers, but that's what I'm getting at with this question when I ask about what the image is. But for all of these, I'm just going to go ahead and write R as the codomain. So this is the function that takes x to e to the x. So this is how we would describe this now. The question is, what things can you put into this function? That is, what are the things from the real numbers, which if I put them into e to the x, I get out something that's not undefined. Note this phrase natural domain is exactly the sense of the word domain from regular calculus, pre-calculus, whatever. It's all the inputs that give you an output. And in the instance of e to the x, that natural domain is actually also all real numbers. I can raise e to any real number power, e to the -7th, e to the 0th, e to the 163rd. All of these are perfectly well-defined things. And so, in fact, the natural domain of e to the x is all real numbers. Now, what's the image of this function? That is, what real numbers do we get out of the exponential function? And the answer here is not all real numbers. In fact, every number I get out of the exponential function as an output is always positive. In fact, I get out exactly the positive real numbers. Again, it's helpful here when thinking about this to think about what the graph of e to the x looks like, and in particular, this horizontal asymptote here at y equals 0. And so that tells you that though you never get out 0, you get out every number greater than 0. So that is e to the x. What about the function natural log? My experience is this is usually the one that people most have forgotten about. What can I take the natural log of? Well, you might remember that natural log is quite related to the exponential function. In fact, what the natural log does is to tell you for a particular input what thing you would have to plug into this other function, e to the x, in order to get that input out. So actually what natural log really does is to reverse the inputs and outputs of the exp function. Now, if you don't remember this or that doesn't quite make sense, don't worry, we're going to talk about that idea a lot, the idea of sort of reversing inputs and outputs to get another function. But in particular, what that means is that the natural log of something is only defined if that something is in the image of the exponential function. And so, in fact, the natural domain of natural log is the positive real numbers, which are exactly the image of the natural exponential function. And that's because these two functions are, as we'll talk about later, inverses of each other. Now, what is the image of natural log of x? Well, in fact, again, because what natural log does really is to swap the inputs and outputs, in fact, the image of natural log of x is all of r. Again, if you picture the graph of natural log of x, it ends up looking like this, where that horizontal asymptote at y equals 0 on the graph of e to the x becomes a vertical asymptote at x equals 0 on the graph of natural log. And so now when I look at the inputs that are allowed, that is the domain, I get all the positive real numbers. But when I look at the outputs, I'm looking now on the y-axis, and I actually get everything. And so the image here is all real numbers. Again, This pair is one we're going to talk about a great deal more later. Just a tiny word on notation, by the way. In calculus, when we talk about a function, we tend to almost always write that function with a variable attached. So that is, in calculus, if I want to talk about the function x, I'm almost always inclined to write it as f of x. But in fact, if you think about it, this x here has never actually been communicating any information, because the name of the variable you put into a function isn't a meaningful part of the function. In fact, f of x and f of t are exactly the same thing. If f of x is x squared, then f of t is t squared. They're the same thing. These are exactly the same function. And so, usually, in this course and in other math courses, when we talk about functions, we're usually not going to put the of whatever variable name, because the variable name is not meaningful. So here we're usually, when we refer to the function, just going to call the function by the name f. And so you might already have seen me doing this. I didn't ask the image of natural log of x, I just asked for the image of natural log, and I didn't ask for the image of e to the x, I just asked for the image of exp. And that is what you're going to find we're going to do with functions. Now, why is it that we make this change? Why is it that in calculus we write it this way if we're only going to swap it around and write it this way in this course? And there are, I think, two good reasons for this. One is pedagogical. That is, in calculus, you're learning what a function is. You're learning to sort of conceptualize the idea of a function as something that is separate from the idea of a variable. And this is made especially difficult by the fact that usually the first functions you write in calculus have the form y equals something, and so y is a variable, but it's also a function, and that's always kind of confusing because it's ambiguous exactly what's going on. And so if we then proceeded to just write f instead of f of x for our functions, then it would be even harder to distinguish between, is this thing I'm talking about a function, or is this thing I'm talking about a variable? Now that you've sort of internalized the idea of functions, because you've been through at least a year of calculus, perhaps more, it's not such a big deal to worry about disambiguating these two things. And so you're less likely to get confused if I write this f and think, oh, maybe he means this f is a real number as opposed to a function, especially if I've spelled it out in gory detail like I will tend to do here. So that's reason one. There's another reason, though, and that reason shows up also in the other places where you tend to write functions of this sort. Namely, a lot of the functions that you do as examples in calculus are connected in some fashion to the real world. So they might be referencing, for example, the velocity of a ball at a particular time, or the height of that ball, or the density of the air in the atmosphere at a particular altitude, or whatever. And when your function is representing something, usually you want to remind people of the thing it's representing. And so usually you will choose a name for the function that reflects that. So if it's velocity, you're likely to call the function v, for example. But just as important in these real-world examples as the thing the function is representing as an output is the thing it's taking as an input. So if you're talking about the velocity over time, then you would very likely, for example, name the input variable t to reflect that it refers to time. And so you would always write v of t, just to remind the person who's looking at this that, hey, we're talking about how velocity changes with time. Or if you were instead talking about how quickly a rock fell through the water based on the temperature of the water, then you might use different letters. You might use a capital T to reflect that it's temperature and not time, and so on. Likewise, in physics or any sort of science, when you're referring to functions, you'll often see them spelled out with what their input variable, or often more than one variable, is, and what their output is. And that's as a reminder of the physical context of the problem. Whereas when we're talking about abstract functions in this course, there is no physical context that we have to remember. So we won't do that, and we'll just refer to the function by its letter most of the time. Okay, so what about sine and cosine? What are their natural domains? Well, again, I can take sine of any number, and I can take cosine of any number. So in fact, both of these, like the exponential function we talked about previously, both sine and cosine have as their natural domain all real numbers. To the point about variables, you might notice that here I described where x goes, and here I described where theta goes, but that has no significance in the function being described. These are both describing, well, they're not describing the same function. This is describing sine, and this is describing cosine. But if I'd used x instead of theta here, or theta instead of x here, it would have made no difference in the function I was defining. This variable is just a quote-unquote dummy variable, meaning this variable x does not hold any specific meaning. It doesn't have any particular value, and so I could use x, I could use theta. The only important thing is I couldn't put this as x and this as theta. If I say x goes to sine of theta, that doesn't make sense. Tangent now is problematic. And the reason why tangent is problematic is that tangent has a bunch of vertical asymptotes. That is, tangent has a bunch of inputs where it's undefined. So what do I mean by that? Things like if I go to take tangent of pi over 2, what's that going to be? Well, remember that's sine of pi over 2 over cosine of pi over 2. But if you remember your trig values, that's 1 over 0, which is undefined. So pi over 2 is not in the natural domain of tangent. Now what this means is that when I go to write down the natural domain of tangent, it's going to be a little bit annoying to describe, because what are the other things that are not in the natural domain of tangent? Well, pi over 2, what's the next one? 3 pi over 2 is the next one, actually. 5 pi over 2, 7 pi over 2, and so on, but also in the other direction. These are all of the inputs where tangent is undefined. Now, really, that's to say these are all of the inputs where cosine is 0. So if I want to write down the natural domain of tangent, I have to really find a way to describe this set. And describing this set, as it turns out, is a little bit annoying. But here's a natural way to do it. Namely, what this set really is pi over 2 plus any integer multiple of pi. And so in our set builder notation, this is one way to describe that. Now note, this is not the thing that is the natural domain of tangent. This is actually the opposite. It's the complement of this set that is the natural domain of tangent. So if you were to write this out, what we should really write is that tangent is really a function that goes from R minus that set to R. This is kind of a horrible mess, and so sometimes people will not use this as the domain for tangent. In fact, a common choice for the domain for tangent is actually to choose only the open interval from minus pi over 2 to pi over 2. And doing this has a few advantages. One advantage is that the domain is much easier to write down. Another advantage that we'll talk about later is that it turns this function into a bijection. But again, we'll save that part for later. But the reason why this isn't such a loss, even though this set is much, much smaller than this set that we wrote up here, is that tangent, like all the trig functions, is periodic. And so tangent, in fact, is periodic of period pi, meaning that it repeats every pi. And so this actually captures a whole period of tangent, and so really for a lot of purposes that you might be considering the tangent for, it doesn't actually matter whether you capture one period or all the periods. And so you'll see, depending on the application, people will either work with this function or this function. Another quick reason why you might prefer this, by the way, is that this function happens to be continuous, whereas this function isn't, because of the vertical asymptotes that are there. Real quick, let's write down what are the images of sine, cosine, and tangent. The image of sine is the closed interval from minus 1 to 1. Sine never gives out anything larger than 1 or smaller than minus 1, but it does give out minus 1 and 1 and everything in between. And the same is true for cosine. Tangent, in fact, gives out all real numbers. And again, that's something that if you think about the fact that tangent has all of these vertical asymptotes, you can picture the graph, and then you'll see that indeed, yes, all real numbers come out as outputs of tangent. Last up on this list, I want to talk about the factorial function. Now, the factorial function, its fancy name is gamma. You certainly don't have to remember that, but I'll go ahead and call it gamma here. And so the question is, what is the natural domain of factorial? That is, what are the things I know how to take the factorial of? And here the answer turns out to be quite unlike all of the other questions we've done before. Namely, the only things I know how to take the factorial of are integers. And not even just any integers. In fact, only non-negative integers. Right? I don't know how to take the factorial of -2. Nor do I know how to take the factorial of something like pi. And so here the natural domain is actually quite strange looking by comparison to the other functions we've listed here. Now, the image of this function is actually even stranger, because how do I describe the set of things that are outputs of the factorial function? Well, I really have no choice but to write that it's really the set of n factorial for n in z sub greater than or equal to 0. There is no better way to describe this set 1, 2, 6, 24, 120, etc. This is really the best description of this set that you're going to find. I'll note, by the way, it's a very natural question to ask if there's some reasonable definition of factorial that you could actually define on, say, the positive real numbers instead of just the positive integers. And it turns out that actually there is, although this function ends up having some quite unexpected properties, and you really need to have a pretty strong understanding of complex numbers to really fully understand and appreciate all of the properties that this function has. So for us, we're only going to talk about factorials of non-negative integers. Now, you'll notice for all of these functions where I've stated a natural domain and the image, I haven't really stated a proof or anything of that sort. These are things you can take for granted. These are things that really go in the definitions of these functions back from calculus, but because you didn't talk about functions in this way in calculus, I now have to give them to you in this capacity. But you do not have to justify why the natural domain of natural log is the positive real numbers, or why the image of sine is -1 to 1, for example. Those are all things you can cite without proof from here forward. I've written down here two things that look notationally correct. That is to say, I've written down two sets, a domain and a codomain, and then I've described what the function does by giving you where an arbitrary element of the domain maps to, and I've used the correct maps to arrow here and the to arrow here. Both of these follow all of that format. And yet neither of these is really defining a function. So I would encourage you, pause the video for a moment and look at both of these and decide what's stopping each of these things from being a function, and to then try to decide what the least invasive thing you can do to change each of these things into something that really is actually a function is. Before I explain how these things break, let's do one example of each of these just to make sure that we're comfortable with what the function is describing. I'll note, by the way, a tiny bit of notation here that I don't think I've commented on before, which is that if the domain of a function is a Cartesian product, technically if I were to write this properly, I would need to say, what is it I'm taking f of? I'm taking f of the ordered pair 3, 1. But mathematicians don't love parentheses quite enough to want to write this like this, so we just agree that when something is stapled like this, that is, there's this pair of parentheses inside another pair of parentheses, or in other words, when the domain here of the function is a Cartesian product, then we just suppress one of these pairs of parentheses, and we write the function like this instead. That is just a notational convention. It doesn't carry any more significance than that. So what is f of 3, 1 here? Well, that should be 3 minus 1 over 3 plus 1, which will be 2/4, which is the same thing as 1/2. Note, again, there is no problem here with what I've written down. Similarly here, when I look at my function g, the input here is meant to be an element of the power set of z+, That is to say, the input here is a subset of the positive integers, and the thing I'm supposed to return here is the minimum element of that subset. So when I go to take the minimum element of this, well, the minimum element here is 1. Again, there is no problem here. Even if I took something like the set that, it's still very clear what's the minimum. It is 3. So that is both of these functions, or functions in quotes, working. Again, if you haven't thought about it yet, try and figure out what's wrong with f and what's wrong with g. So let's look at f first. And your eyes should be drawn pretty immediately when you look at f to this denominator. Because we've done a number of examples before where it's turned out that the problem was that you ended up dividing by 0. And so if you divide by 0, you get undefined, and that does not work out so well. However, if you look closely at this, you will see that this was actually a bluff, because in fact the domain specifies that I'm only allowed to take x and y positive. Not 0, but strictly positive. And so when I add x and y, in fact, I always get something positive, so in fact, x plus y, this is never 0. So though that's where your mind is drawn, or where your eye is drawn, or whatever, it's in fact not actually what's wrong here. So what is wrong here? What is wrong here is actually what's specified as the codomain. And that's because the codomain here is telling me you're going to put in a positive real number and a positive real number, and you're going to get out a positive real number. But in fact, because of the numerator of this fraction, there is no guarantee that you are going to get out a positive real number. For example, if you took f of 1, 3 instead of f of 3, 1, this formula would helpfully tell you, oh hey, what am I going to get out? I'm going to get out 1 minus 3 over 4, which is minus a half, but that is not a positive real number. And so, regrettably, this does not end up defining a function. So how do you fix this? Well, I think the best way to fix this is probably to just change the listed codomain. And this will give you a real honest function. Here's another thing you might consider, namely, leave the codomain the same, but fix the fact that the numerator here can be negative by putting an absolute value around the x minus y. And so if you look back here, our problem was that when I took f of something like 1, 3, it worked out to be negative a half. But if I used this definition, then f of 1, 3, because of this absolute value, actually becomes positive a half, and it's really in the positive reals. And so you might think of this as a different way of fixing up the function f. So if I convinced you, is this really a function? Is this an alternative way to write this? Well, sadly, no. This is still not a function. If you don't see it yet, take a moment. Why is this still not a function? And the reason it's still not a function is because of 0. But not 0 in the denominator. We said that could never happen because both of the inputs happen to be positive. But actually, it's still possible for there to be a 0 in the numerator. And so if I took something like f of 2, 2, that will in fact be 0, because I'll get 2 minus 2 over 4, which is 0. But that 0, that's not a positive real number. And so this is not a function. As a result, if you want to fix this without changing the listed codomain, you actually have to butcher the domain quite a bit. And so, if you really do have your heart set on leaving this as an R+ in the codomain, then what you can do is you can replace the domain with this, that is with the set of pairs xy where the x is bigger, And then you can write down this function f from this to r plus that takes xy to x minus y over x plus y. And now, because of the condition that x is greater than y, x minus y is actually still positive, and so this is actually a function. So now, a really natural question is, okay, so that's two ways to do it, but which one's right? Is it this one, where we changed the codomain? Or is it this one, where we changed the domain? And the answer is actually that neither is right. There's no well-defined sense in which one of these is most like the original thing that was not quite a function. Depending on why you happen to be considering this thing that wasn't quite a function, you might prefer this one or you might prefer this one. They're both options. Let's go back to the second example now. So in the second example, I wrote down again, function in quotes, because it's not really a function, from the power set of the positive integers to the positive integers. And what it purports to do is to send each subset of the positive integers to the minimum element of that subset. The problem here is really subtle, so you should not feel bad if you missed it. But the problem here is our old nemesis, the empty set. Namely, the empty set is definitely an element of the power set of Z+, and so you should be able to take G of the empty set, which, by definition, is supposed to be the minimum element of the empty set. But this has a problem, namely there aren't any elements in the empty set, so it definitely does not have a minimal element. So the problem here is that, in fact, we have an element that's listed as being in the domain, but where the thing I wrote down is actually undefined. So going all the way back to the first example, if you were expecting that what was going to turn out to be the problem was that I was dividing by 0, actually, what happened here is very similar to that. I ended up taking a minimum of a set that doesn't have any elements. So I can fix this, in fact, in a couple of ways. To my eye, the most natural way to fix this is to just throw the empty set out of the domain. Note here, again, I need set brackets around the empty set because I actually want to be subtracting the empty set as an element from the power set of Z+. If I didn't have these set braces here, I would be saying take away nothing. And if you take away nothing, well, you're going to get the set you started with, which is not what I wanted. So what are other options? Well, other options involve deciding what you actually think this function should be on the empty set. So you might, for example, decide that when you input the empty set to this function, you're going to give out 7. And so you might write something like this. And this is just your plain old piecewise notation going all the way back to calculus days, where I've specified, okay, depending on what the input is here, in this case I've chosen S as my input, what do I want the output to be? And in this instance, I've just said, oh, well, I want the output to be the minimum of S, unless S was this really problematic set, the empty set, in which case I'm just going to say, okay, the minimum is 7. So this is perfectly fine. This is also an answer. However, this feels really artificial to me. And so I probably really want to write down something like this, where if I'm going to say the minimum of the empty set is something, I probably want to actually say something like the minimum of the empty set is 0. That feels a little more reasonable. However, here we've fallen into the trap again, because now, just like the original version, I've defined the empty set to be something that's not actually in the codomain. Namely, 0 is not a positive integer, so this doesn't work. And so if I want to fix this, I would actually have to change the codomain to include 0, and so say, okay, well, if S isn't the empty set, we'll send it to the minimum of S, and if S is the empty set, we'll set it to 0. And so again, this is another actual function. This is a perfectly fine answer here. Again, neither of these answers is more correct. There's not a well-defined most correct answer, but I think both the first answer here where we took out the empty set or where we said, okay, we're just going to send the empty set to 0 and bump that into the codomain, I think both of these are very natural answers to this question, depending on what it is we're actually doing. I often get the question, by the way, is a piecewise function still a function? Like, am I allowed to define functions this way? And things like this are just as much functions as any other functions. Back in calculus, when people define functions, they often say something like a function is a rule for doing blah, 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 which implies that there's some sort of structure to it. Because if it's a rule, it implies that there's some one thing that you can do to each element to get the output that you want. But that whole idea of the function being a rule, that was not at all part of our definition of a function. Our definition of a function just said where I'm assigning one element of the codomain to every element of the domain, and that assignment can be as organized or disorganized as you want. It could be totally haphazard and random. That doesn't stop it from being a function, as long as exactly one element of the codomain is assigned to every element of the domain. So I'm going to write down two just slight twists on the example we just did. So we just again showed that, hey, if I take the power set of Z plus aside from the empty set, and I take each set to the minimum element of S, that gives me a function. And so here I've made two changes. In F, I've made the change where I've replaced the minimum with the maximum. Seems simple enough. And in this example, I've replaced the Z plus with an R plus. Again, seems innocuous enough. But again, both of these fail to be functions. And so I'd again like you to pause the video and take a moment to think about what actually stops each of these things from being a function. So let me spoil for you what's wrong with each of these. The problem with this first one is that though every non-empty subset of the positive integers has a minimum, not every subset of the positive integers has a maximum. And why is that? Because I could try and take something like the set of powers of 2. That's a perfectly reasonable subset of the positive integers. But unfortunately, despite being a subset of the positive integers, this set does not have a maximum. Indeed, the problem here is that in general, no infinite subset of the positive integers is going to have a maximum. And, well, that's going to mean that this thing's not a function. So I've mentioned this before, but I'll mention it again. It is an essential property of the positive integers that every non-empty subset of the positive integers has a minimum element. However, there are plenty of subsets of the positive integers that do not have a maximum element. So if you wanted to try to fix this, you would need to insist, for example, that the sets you were looking at were only the finite subsets of the positive integers. And I really just here want to emphasize the power set, if your set is infinite, contains plenty of infinite sets as well. So what's the problem in the second example? I've left this as minimum. So what's the issue here? And here, the problem isn't with minimum, the problem is with the real numbers. Namely, there are subsets of the real numbers that do not have a minimum. And so, for example, what if I take the open interval 2, 3? Now, earlier I mentioned how if we put parentheses in parentheses, we just suppress the second set of parentheses. That's only if the first thing is a Cartesian product. Here, that's not actually what's happening. Here, this is actually the subset of the real numbers that looks like this. And so to emphasize, this is still a set, not an ordered pair. We're still going to leave the parentheses here. I know these notational conventions are a little weird, and it takes a while to get used to all of the conventions. And one of the things that makes that trickiest is that as mathematicians, we tend to internalize these, and so we may forget to remind you of some of these conventions that we've all sort of accepted in our brains. And additionally, some of us might have internalized different agreements about these particular things. So again, that's the difficulty with conventions. But anyway, once I actually think about it, what is the minimum element of this set? And the answer is there isn't one. Because in a sense, the answer really wants to be 2, except 2 can't be the minimum element of a set because 2's not an element of the set. However, I can get numbers arbitrarily close to 2, so I can't pick any number larger than 2. That won't be the minimum either. So in fact, this is undefined because this set has no minimum element. This problem with the real numbers turns out to be a very serious one, and when it comes time to really dissect what's going on with the mathematics of the real numbers, that is, when it comes time to understand calculus and derivatives and integrals and continuity and all of these things that are sort of really wrapped around the idea of the real numbers as opposed to the integers, this problem ends up being a nightmare. And so actually, a lot of the 1900s was spent by mathematicians basically figuring out how to rigorously, rather than intuitively, deal with the real numbers and deal with this kind of problem. I think that's a really awesome story, and in fact, that's the story that gets told in Real Analysis. So if you're interested in hearing that story about how mathematicians sort of took this idea of calculus from physicists, where it wasn't really rigorous and well-defined, and actually transformed it into something that is axiomatic and well-defined, and there's proofs and proper definitions of everything with quantifiers, I really recommend Real Analysis. I think it's a really interesting class that really forces you to think back on stuff that you understand, and understand it in a new way, from a new angle. So enough of things turning out to not really be functions, at least for lecture. You'll probably find some on the homework. But for here, I'm now going to take something, this just really is a function. You can take my word for it. And so my question is, once I look at this function, which takes a pair of positive integers and turns it into a rational number in the following semi-complicated way, is the number 2/11, which I chose seemingly at random, is that number in the image of this function, yes or no? That is it possible to get 2/11 out of this? And just to make sure we understand what this function's doing, what do I get if I take f of 5/7, for example? Well, I'm going to put the 5 in the numerator, and then the 7 in the denominator in the power of 2. 2 to the 7th is 128. So this is actually going to be 5 over 129. And that will be our output. And so my question is, hey, can I do something like that, where instead of getting out 5 over 129, I get out 2 over 11? Now, there's a really natural thing to do here, which is to say, what am I really doing? I'm trying to decide, hey, can x over 2 to the y plus 1, can that equal 2 over 11? Well, that's to say, well, I want x to be 2, and then I want 2 to the y plus 1 to be 11, and then I look through and I see, okay, well, 2 cubed plus 1 is 9, 2 to the 4th plus 1 is 17. And so I see, oh, well, I can't actually get 2 to the y plus 1 to be 11. That's not an option. And so then it looks like, okay, the answer is no. But I want to warn you, rational numbers are slipperier than that. This does not work. Why are rational numbers slipperier than that? Well, rational numbers are slipperier than that because if I were to instead take, for example, f of 9, 3, what will I get? Well, I'll get 9 divided by 2 cubed plus 1, which is 9 over 9. But I would very rarely think of the rational number 9 over 9 as being 9 over 9, because in fact, that happens to just be 1. And so 2/11 describes a rational number in lowest terms, but it does not, in fact, describe 2/11 in every possible way of writing it. And so, yes, it's true. It's not possible to get x to be 2 and 2 to the y plus 1 to be 11, but it is still possible to get 2/11 out of this function. With that hint, I encourage you, pause the video for a minute, it shouldn't take you too long, figure out what actually will give you 2/11 out of this function. So how can I approach this question? One way to approach this question is to think, okay, well, I can't get out 2/11. Well, what other ways are there to write 2/11? Well, I could write 2/11 as 4/22. I could write it as 6/33, as 8/44. And so I could think, hey, is there a way to get x to be 4 and 2 to the y plus 1 to be 22? Well, no. Is there a way to get x to be 6 and 2 to the y plus 1 to be 33? And in fact, there is. And the reason why is because 33 happens to be 1 more than a power of 2. And so is 2/11ths in the image of this function? Yes. F of 6 comma 5, you can check, is 6 divided by 2 to the 5th plus 1, which is 6/33, which after I cancel is 2/11ths. And that is enough to prove that 2/11ths is really in the image of this function. I want to think a little bit about what it takes to describe a function. And so I want to think about all possible functions between some particular sets. So to start with, let's ask the question, how many possible functions are there from the set heart to the set diamond, club, spade? And so if you picture back to our little dot diagrams, we have heart here, then we have diamond, club, and spade over here. And what do I have to do? I have to draw one arrow from this heart to one of these three things. And actually, that will completely describe the function. Namely, this is described entirely by what happens to heart. And what's special about heart, the thing that's special about heart is that heart is the only element of A. And so a function is really three things. It's the input set, the output set, and where each element of the input set goes. That is an assignment of each element of the output set to the input set. And so in this case, once I choose what f of heart is, I've completely described the function, and there are three options. F of heart could be diamond, f of heart could be club, or f of heart could be spade. So in total, there are three functions. Note this gets a little more complicated if instead there's two elements over here. Now, in order to describe a function from heart and 3 to diamond, club, spade, I would need to say where heart went and where 3 went. And there are three options for where heart would go, and also three options for where 3 would go. And so in fact, in this case, if I had asked this question, there would actually be 9 functions. 3 choices for heart, 3 choices for 3, and I could multiply the 3 and the 3, and that'll give me 9. Let's mix this up a little bit. And so let's talk about our nemesis, the empty set. So I'm going to keep the same set B. So that is, B is still the set diamond, club, spade. But my question now is, how many functions are there from the empty set to B? And how many functions are there from B to the empty set? Again, I encourage you pause for a second. Think about this. And I'll tell you, before I tell you the answer, for one of these, the answer is 0, and for one of them, the answer is 1. Try to decide which is which. I think the more intuitive of these is that there are 0 functions from B to the empty set. Why is that? Well, in order to be a function from B to the empty set, what do I have to do? I have to tell you where each element of B maps. Where does diamond map? Where does club map? Where does spade map? And these question marks, they all have to be filled with elements of the codomain. That is, they all have to be filled with elements of the empty set. Except, well, there's really only one thing to know about the empty set, which is that it doesn't have any elements. And so there are no elements that I can put in these places. And so that ends the fantasy of a function from B to the empty set. In fact, this really ends the fantasy of a function from any set to the empty set, with the sole exception of a function from the empty set to the empty set, which I'll promise I'll talk about in just a moment. What about a function from the empty set to B? So that is, for all of the elements of the empty set, I have to assign one element of B. And as soon as I assign to every element of the empty set an element of B, then I'll have defined a function from the empty set to B. Except I've written blanks here for my elements of the empty set. Why? Because, again, there are no elements in the empty set. So in fact, as soon as I've done nothing, I have already assigned an element of B to every element of the empty set. Because, well, satisfying a condition for every element of the empty set is very easy. However, because writing down an element of B for every element of the empty set is so easy, there's only one way to do it. Because there weren't really any choices that I was allowed to make. And so, in fact, there is exactly one function from the empty set to B. Now, this is weird, and so then it's extra weird if I then ask about functions from the empty set to the empty set. And so if you think about the logic over here, and you think about the logic over here, you might think that there's a conflict about whether the answer for the number of functions from the empty set to the empty set is supposed to be 1 if this logic applies, or 0 if this logic applies. But which side has logic that actually does apply? Well, if you think about it carefully, because I know this is confusing, this logic over here actually does not apply to functions from the empty set to the empty set. Because really, the logic over here was, okay, well, I don't have anywhere for diamond to go, so there can't be a function here. But in particular, this was all predicated on the idea that I needed to send diamond somewhere, or club, or spade. However, if I'm looking at a function from the empty set to the empty set, I don't have any elements in the empty set in the domain that I need to assign an element of the codomain to. And so, in fact, there is exactly one function from the empty set to the empty set. And that one function is the function that, well, doesn't do anything. All right, I'm going to wrap up this video of examples here. In the next video, we're going to start diving into properties that we might want functions to have. So we're going to talk about one-to-one functions and onto functions, and eventually bijections, and inverse functions, and function composition, and all of these other properties and things that we're used to doing with functions from calculus, but we're going to talk about them in this broader context of this kind of function. But that's enough for this video. I'll see you next time.